Hi everyone, welcome to Chemistry Insight. In this particular video, I am going to discuss about Baeyer-Villiger oxidation. This reaction is a chemical reaction in organic chemistry where ketones are converted into an esters or cyclic ketones are converted into an lactones in the presence of peracids. That is, we can write it as here on the arrow I will write peracid. Before they were using per-monosulfuric acid as the reagent, and afterwards three major reagent came into existence, that is perbenzoic acid. I am talking about this per acid here perbenzoic acid and peracetic acid, and here trifluoro peracetic acid peracetic acid. The structure of this three reagent will contains peroxide linkage, that is O will be there, and here like that. This is acid, and here R carbonyl group will be there, and here any R group. Suppose here if phenyl group is there, then it become perbenzoic acid. If here CH3 is there, then it is peracetic acid, and here CF3 if it is there, then it will become trifluoroperacetic acid. And now we'll see how the mechanism will work in case of Baeyer-Villiger oxidation. A general example, I will be taking a unsymmetrical ketone. Here R prime will be there, and it is a reversible reaction, the first step, and here I will write per acid like this. This is per acid. I want to discuss one thing, that is the main reagent which is used in case of Baeyer-Villiger, that is MCPBA we will use. That means here at the meta position chlorine will be there, and here benzoic acid, peroxybenzoic acid will be there like this. This famous reagent is called as metachloroperoxybenzoic acid. This is came into existence because it is commercially available and it is very easy to handle compared to others. Compared to other reagent, it is in the lab we can use in better way. That's why this reagent is famous in case of Baeyer-Villiger oxidation. And here in general example I will be taking in mechanism, and oxygens have two lone pairs, correct? Here also two is there, and two lone pairs is there. And here what will happen, this lone pair is there in conjugation with this particular carbonyl group. That's why whatever the terminal oxygen is there, this oxygen lone pair is localized over here, and this particular lone pair will come and attack this particular carbonyl group, and electron will shift like that. Then we will get it as R will be there as it is, and here R prime, here O minus, and then oxygen and one hydrogen. Since it donates pair of electron, it has to get a positive charge, and over here oxygen and carbonyl group is there as it is, and like this it is there. In the next step what will happen, this one also have one lone pairs. Now what will happen, charge neutralization has to be done. Here this anion will abstract this particular proton, and charge neutralization of oxonium ion will takes place, and here we will get R, and here R prime, here oxygen is there, and here hydrogen, and here I will get oxygen, here carbonyl group, and here R double prime. This is the intermediate we will get in case of Baeyer-Villiger oxidation. Now this step is very crucial in case of Baeyer-Villiger oxidation, and here the rearrangement will happen, that is in concerted way. What will happen is the lone pair which is present on this particular oxygen, it will move like this, and this whole R prime, whatever it is there, it will shift like this, 1 to shift, and this group will leave as acetate, or in general, they, it depends on R. Like carboxylate ion will leave this particular moiety, and finally we will get here R will be there, and here R double bond O and hydrogen. One positive charge is there, one lone pair. Then further it is attached to oxygen and R prime. Then what is the byproduct we got over here? This bond already broke over here. Then we will get R double prime and C double bond O and then O minus. Now what will happen is this particular negative charge will abstract this particular hydrogen proton, and now charge neutralization will happen, and finally we will get R C double bond O and oxygen and R prime. If we observe the reactant, whatever it is there in the beginning, we will see that this is the particular reactant is there. Now if we observe this product, what we can observe is oxygen is get inserted between this bond like that. Now in the transition state, we saw that here what is happening is this group, whole group is there, it is leaving, it is carrying a negative charge. If the negative charge is carried away by this group, and this whole group will become some positive nature will be there. If positive charge is spread over this transition state, this R prime, whatever the group is migrating, it has to take a responsibility in order to stabilize the transition state. That's why what is the inference is, if R prime is more electron donating group, more is the migratory aptitude. More is the migratory aptitude. That means it have a greater tendency to migrate over this particular oxygen. If R prime is more electron donating group, definitely this one will migrate rather than this R. Suppose if R prime is electron withdrawing, this group will not migrate. Rather than this R group, whatever it is there, it will migrate. Like that we can observe. And in the next step, we will see what is meant by this migratory aptitude. What is the sequence of this migratory aptitude? Now, I will give the sequence over here. If we take in general, the tertiary alkyl group is there, it will show a maximum tendency. Then it will come for cyclohexyl. Cyclohexyl group, this is almost equal to secondary alkyl group, and this is also almost equal to benzyl. This is benzyl will be there and almost equal to phenol. Finally, we will get primary alkyl group, and at last we got methyl group like this. We can observe over here, in case of alkyl groups, tertiary will have the maximum tendency of migration, and then secondary, then primary, then methyl. Wherever we will find a tertiary carbon, and here we attached carbonyl group and here primary, definitely this group will migrate. That means oxygen will get attached. Suppose here like this, the product will come afterwards. Like this it will be there, oxygen will get insert in between tertiary carbon and this particular carbonyl group. Now we'll take up an example. Suppose if I take acetophenone as an example, here I have pH double bond O and here CH3 is there. This is acetophenone. If I add MCPBA to this in the presence of acetic acid under 0 degree Celsius. Now what I will get in this sequence, we already observed that the phenyl group is there. It will show a maximum migratory aptitude compared to a methyl group. Correct? That's why here what I will get, the oxygen will get inserted over here. Correct? I will get the product as pH and oxygen, further carbonyl group, and CH3. This is phenyl acetate. We will get it as a major product. Now, further this, if you want to hydrolyze this particular product, whatever we got, that is acid hydrolysis, if I want to do, then what will happen? This is an ester. Hydrolysis of ester will lead to an acid as well as alcohol. This bond will break, correct? Now, what I will get is PHOH, that is simple phenol I got, and over here acid I want to write like CH3C double bond O and OH. This is acetic acid. Now we'll move on to the next example. This is the second example I'm giving over here, which contain a cyclic ring, that is cyclopentanone. With in alpha position we have methyl group. Now what we have to do is, first of all we have to try to understand here tertiary carbon is there, the type of carbon adjacent to this particular carbonyl group. Here tertiary carbon is there and here primary is there. Now between this tertiary and this primary we will get a maximum migratory aptitude for tertiary carbon. That's why we will get it as here cyclohexane. This ring I will write like this, and here oxygen, and further like this. This is 6-membered ring. Better in way I will write it as like this. I will write, and here methyl group is there as it is. This is the product we got after adding per acid, any per acid. Now to this one, if I want to add lithium aluminum hydride, then what is the product I will get over here? Lithium aluminum hydride is a reducing agent which will reduce this ester to an alcohol, correct? This bond will break over here. This particular group converted into OH, as well as this one also as OH. Now I will write it as here methyl group is there, and this group I am writing over here, OH. 1, 2, 3, 4. This is 1, 2, 3, 4, and then OH. This is the product. Now I will try to do a different example. Now what is happening here? Here it is peracetic acid is there over here, and here we have a quaternary carbon over here, and here we have a primary carbon. Now what will happen? The oxygen which will insert over this particular bond, and finally we will get it as like this. Here oxygen will be there and like this, and here carbonyl group, and here methyl group is there as it is. This is the particular product we will get. And over here this is epicamphor. This is not a camphor. For camphor the carbonyl group will be present over here. This is epicamphor, that is the position of this carbonyl group is changed, correct? In this case we will get, actually this is the tertiary carbon over here, and here we have primary carbon. Now what will happen is, this there is a steric hindrance which is coming over here on the top face of this. There is a 2 methyl group is there on the 7th position, which will leads to steric hindrance. Because of that, what will happen, the whatever the per acid is there, oxygen will come and attack over this position, and the product we will get it as like this. Here oxygen will get insert, and here carbonyl group is there as it is, and like this we will get. This is the major product we will get in this case. Now we'll see another example. Over here we have got double bond is also there, and here carbonyl group is there, and also the reagent m-chloroperbenzoic acid. Per acid can do two work, that is epoxidation over double bond, or it can lead to normal Baeyer-Villiger oxidation. It can do. In this case the both is possible, but the major one we will get it as a Baeyer-Villiger oxidation. Here is the tertiary carbon and here is the primary. Definitely oxygen will get inserted over here, then we will get a product as like this. Here carbonyl group is there, double bond is there as it is, and here methoxy group is there. After NaOH they are given. What this means, base hydrolysis they are given over here, and finally what will happen, this is an acid, this is an ester. After hydrolysis it will become alcohol as well as an acid. That's why the product, final product, we will get it as like this, and here OH is there and one carbon, and this is the carbonyl group, C double bond O, OH, and here OMe is there. This is the final product we got, and double bond is there as it is. This is the final product. If we want to write in normal way like this, we will write it as, see this one, hydrogen is there in this case away from the observer. This is hydrogen, and towards the observer there is methoxy group here. And these two groups I have to write away from the observer, that is OH, as well as here one carbon and here COOH. This is the major product we want to write. Then we'll take a different example, which is this one. Now here what is happening is, here also there is a two case. Here double bond is there as well as carbonyl group is there. It can do two work, that is epoxidation or Baeyer-Villiger oxidation. In the first step, what will happen is epoxidation will be the major product, that is we will get, after epoxidation we will get the product as carbonyl group is there as it is, and here this 2 methyl group, and finally we will get an epoxide ring like this. This product will be 89%. Suppose if we add this particular reagent as in Baeyer-Villiger oxidation, this is bis trimethyl silyl peroxide. When we add this particular reagent with boron trifluoride, we will get a Baeyer-Villiger oxidation in the major amount. That is, oxygen will get inserted over here, and finally we will get a lactone, six-membered lactone, and over here we have like this. Double bond is there, unaffected as it is there. Now, another thing is, when we observe this one, salicyl aldehyde, this is salicyl aldehyde. Here we have hydrogen peroxide, correct? Hydrogen peroxide we will write like this, and NaOH is there. NaOH means it is a base. Base will abstract this particular proton, and the negative charge will come over oxygen, and this group, whatever the oxygen, this group is there, it will go and attack this particular carbonyl group and the shift like this. Now what we will get is like this. Here phenol group is there as it is, and I will write it as here O minus, and here hydrogen I will not write, and here oxygen like this it is there. Now what will happen, this group will migrate like, will come like this, and this whole group is there, it will migrate like this, and finally OH minus will leave. Now what we will get, first of all I will write this particular group, phenolic group I will be writing over here like this, and this group is attached to this particular oxygen. Here oxygen is there, this oxygen is attached to this particular carbonyl group, and here one hydrogen is there. I have not shown over here, one hydrogen is there, that is this one. Now after hydrolysis, this is an ester. After hydrolysis we will get a formic acid, and this particular alcohol I will write over here, that is orthodihydroxy alcohol, that is called catechol, we will get as the major product. This is one of the most important reactions where we will prepare the catechol from salicyl aldehyde. Now, another important thing is, suppose if I have a chiral carbon, that is, I will be taking as phenyl group is there, and here carbonyl, and here methyl. Here methyl group is there, and here it is having S configuration. Here this configuration is S. When we will treat this one with benzoic acid, peroxybenzoic acid, we will get, definitely the oxygen will get inserted over here. I will be writing it as like this, like this. And here what will happen, the whatever the configuration, yes, configuration is there, it will remain unchanged. Retention of configuration we can observe over here. This is all about Baeyer-Villiger oxidation. I think this video was helpful for you people. Thank you very much for watching.